Hi, welcome back to Advanced Strategy and Analytics. In this assignment, we're going to be going over how to do a regression, how to create a regression machine learning model. So let's get started by first creating a new Jupyter notebook file. I am going to call this assignment 5 regression. Awesome. Okay, the first thing I'm going to do is make a new text header, and I'm going to call this, or actually before I do that, I'm just going to kind of walk through, give you an idea of what we're going to be doing in the code. There's going to be a couple things, there's going to be a couple headers that we are going to want to have. First, we will have import. We want to first import our data. Then after that, we are going to do data cleaning, which is going to prepare our data to be able to be trained on a model. So that'll include just dropping whatever columns we need to, creating dummy variables, and splitting the data up between a training set and a testing set so we can gauge the accuracy of our model. And then we will actually go ahead and do the analysis, or this is going to be where we train our model. And then finally, this is going to be for the extra credit. We are going to do model tune. We'll go over model tuning. So hopefully that gives you an idea of just kind of the general overview of the walkthrough of what we're going to do with the code. But let's get started with importing. So first we want to import our libraries. We want to import pandas so we can manipulate data frames. And then we're going to import our Seaborn, which has our data sets that we'll be calling from. So I'm going to go ahead and import those two libraries. Then I'm going to make a data frame. I'm going to make it equal to seaborn.load dataset iris. I'm going to call the iris dataset. Okay, and here we have our dataset. So we're ready to get to move on to data cleaning. So the first thing that we notice about this data set is that we have this column right here, which is a categorical column. Now, our regression algorithm cannot handle text data like this. It can only handle number data. So what we're going to do is we're going to change this text data into a numeric form that can actually be interpreted by an algorithm. So I can use a function called get. I can use a function that pandas has called get dummies. If I run that on our DF, on our data frame, you'll see what this function does is it takes this column of text and it splits each of the different instances or all the different types of value of this single column into 3 different columns. So if a species or if an observation has this column, then it'll give it a 1. If it does not have this categorical variable, then I'll give it a 0 and so forth. I also want to mention in this step, we don't have to do it for this data set, but in other data sets, you might have some columns such as like an ID field or a name field, so forth. And this is the stage you would want to drop that before you do this dummy. So I'm going to make a comment here. Drop all unneeded columns like name and ID. Okay. Cool, this is a pretty clean data set, so we're not going to spend too much time on it with the data cleaning. So I'm just going to call this df ready, or this is going to be our ready data set. Okay, now I am going to go on and I want to split this up between our independent variables and dependent variables. In this particular exercise, I am interested in petal length. I want to know what are the effect of all these other variables on petal, or I want to make a model that takes the inputs of all these other variables and predicts for me what the length of a petal is going to be. So I'm going to make a new variable and call it target. Get, and then I'm going to make that equal to petal length. And then I want to state what my target variable is, and I'm going to call that target variable y. I'm going to use df ready, and then I'm just going to mark it as the target. And what this will do for me is it'll tell me what my target variable is. Then I'm going to do an uppercase X. And the reason why I'm doing an uppercase X, it's usually standard convention. I'm not too sure of why, where it specifically comes from. I think before your explanatory variables are normalized, you usually keep it as an uppercase X, and then after you normalize your variables, you change it to a lowercase x, but I'm not particularly sure. All I know is in just about every single machine learning tutorial or class I've gone through, they've always kept all the matrix of explanatory variables as an uppercase X. So now I'm going to find what my X values are going to be, is also going to be df ready, but then I want to drop my target variable. So I'm going to drop columns, and then I'm going to drop target. Drop columns. Okay, and run that. And then if you look at our Y, you can see that we have petal length. And then if we look at our X, you can see we have everything but petal length. Okay, so the last part of our data cleaning before we can get into our model is we want to split the data. And the reason why we want to split the data between a training set and a testing set. So we can train our model on the training set and then evaluate our model's performance on the testing set. Because if we don't do this, if we just train all of our data on, if we just have our model train all the data, we have no gauge to know how accurate our model is. So in order to train, I'm going to import from scikit-learn, I'm going to import model selection, and then I'm going to import train test split. And so this is a very funky function here, so just bear with me. But you're going to make an uppercase X train, then you're going to make a comma, and then your second variable is going to be, a uppercase X test, and then you're going to have a lowercase y train and a lowercase y test. Okay, and now I'm going to call this train, I'm going to call the train split, and I'm going to take our X and our Y, and then I'm going to give it our test size. And I'm going to set this equal to 0.3. And what this is saying is this function is going to take this data set, divide it up, and divide randomly sample, and give 70% of the data set is going to be dedicated to training, while 30% of the of the data set is going to be dedicated to testing. And to come up with this number, it really does just take intuition and knowing your data set and some playing around with. But for right now, all you need to know is what impact that this number has on this data. So if we go ahead, we can look at these different variables. Now, if I go to X train, you'll notice this is 150. Now this is 105. That is 70% of this data set. And then if I go to X test, you see that this only has 45 different, it only has 45 columns. So therefore it's about 30% of our data. So that's what that function does. It's very important for later in our analysis. But let's get on to training our model. So everybody thinks that machine learning is incredibly complicated. And the truth is what goes on behind the hood is very complicated. What the algorithms do is completely fascinating mathematics. However, the reality is people have built out libraries and packages, and when you do machine learning, all you have to do is call one of these libraries and use an algorithm from the library, and it does all the work for you. The training of the model is not the hard part at all. What's the hard part is everything that comes before it, going through this whole data cleaning process to get to a place where you do have data to train a model, and then the post part of the model, which is tuning the model or making it more accurate and fixing it. So let's get into training our model. We are going to import from scikit-learn. We are going to use a linear model, and I'm going to import linear regression. Just make sure that import's fine. Awesome. So now we're going to create our model, and I can call linear regression, and then I'm going to fit this linear regression model, and I'm going to fit it to the training data that we have, to our X train data with our Y train data, and run it. And there you go. We just made a machine learning model, 2 lines of code. So now what we can do is that we have our model. We can go ahead and see how our model works. So I'm going to make a new variable called prediction. I'm going to make that equal to model.predict. And then I'm going to use our X. I'm going to test our model on our X training set. And so what this is doing this prediction function, it's taking our test data set and it's running it through this model we trained, and it's saying, given this this explanatory variable is, what is the target variable we are going to get? Or in this case, given all of these features, what is the expected petal length going to be? And so I can run that, and that returns an array of our what the predictions are. And then I can also make another variable called actual, and I'll make that equal to y test. And you don't have to make variables like this. You can just leave it as y test if you want it to. I'm just doing this to make it a little bit easier to understand if you don't have experience with working with algorithms like this. But this is our actual results. So from here, what we can then do is we can make a model output data frame. And I'm going to make that equal to pandas.data frame. And then I'm going to make our data equal to create a dictionary, our prediction. is going to be equal to the actual, or I'm sorry, prediction is going to be equal to prediction, then our actual is going to be equal to actual. I'm going to run that. And now we can see these two columns side by side. So we can see that here the model predicted that the petal length should be 1.6, but the actual model length was 1.3. So that was a little bit off. But hey, this one was a little bit closer. It said the model length, it said the prediction was 1.4 or almost 1.5, and here we have it as 1.4. So another pretty easy thing we can do with this is we can create this new column called error, and we can make that equal to model output prediction, and then we can subtract that from model output actual. And now what this does is this shows us what our error is, or what is the difference between our predicted and actual results that we have. So now going on to interpret this, what we can do is we can use our describe function on our error. And then we can get this, which is the mean of all the errors put together. So this is what our mean error is right now. What that looks like. However, the reason why I didn't just use the mean function though is I think it's important to look at more than just the mean error because you also want to see the standard deviation. Because something that could happen is all these negative numbers and all these positive numbers can potentially cancel each other out. For instance, if I had two observations and I wanted to get 50 was the actual for both observations, and my first observation was the prediction was 100, and my second observation, the prediction was 0. Well, the error for the first observation is 100 is plus 50. The error for the second observation is minus 50. Therefore, the mean error comes out to be 0, which is not very good because it's not a good describer in that case of what our model is actually doing. So there's something else we can use, and this is a very common way to measure error in machine learning, or we can use something called the mean the mean squared errors. And what this does is, so what all our function did was it took the error and then it divided it by n. That's essentially what we're doing here. This makes it a little bit more complicated. This takes it a step further and squares this function, the error, and then it sums up all of the errors and then finds the mean of the sum of all the squared. It finds the mean of all the squared errors. So in our previous problem, what this will do is it will prevent negative and positive numbers from offsetting each other. And squaring is kind of it's a way of getting mathematically the absolute value. Now, there are a lot of other ways to judge error of a machine learning model, of a regression model like this. I'm not going to get into those. Doing for instance, you could take the absolute value of these two numbers, and you might be thinking, why isn't that the most common way? Is just taking the absolute value of error and dividing that by n. I'm not the best one to speak to this because I do not have too much experience with modeling. However, I do know a common reason that people choose to go with the squaring method is because you can actually it's a lot easier to take the derivative of a squared function than it is to take the derivative of an absolute function. And and if you can easily, or if you can more easily take the derivative of a squared function, it makes it a lot easier to optimize. So if this is our error function and we were trying to find the minimum of error, what I'd have to do is I'd have to take the derivative of this error function and set that derivative to 0 to find the local minimum of our error function, and that would tell me where the error would be minimized. So that's pretty straightforward to do in a squared function, because I just bring down the 2 here, and then this, and multiply the derivative of this function would just be 2y minus 2y prime or 2y hat. However, with an absolute function, taking the derivative of that can get very complicated, and that's why when you're trying to optimize for minimum error, why the mean squared error, I think, is most likely why it's so commonly used, is just for optimization purposes. But going back to that, we can find the mean squared error. We can plug in that function, or we can make our own function like that if we want. However, I think it's much easier if somebody else has already put in the work to just use their work. So we'll import metrics from scikit-learn, and then we'll import mean squared error. And then I'll take mean squared error and I will apply that to our actual versus our prediction. I'll run that, and there we go. That gives us our mean squared error. One other thing we can do for fun, really quick, to better know a visual way to kind of see the error of our model, is if we go to output dot plot, we can go to kind, we'll set the kind equal to scatter, then x equals prediction, and then y equals, or actually we'll do our control variable as actual and our output variable as our prediction. And if I run that, you see I get this scatter plot here, and this is a great way how to quickly visualize the error of this machine learning model. Basically, the closer that this is to a straight line, the better the error, or the more accurate my model is. And I also want to let you know, for those of you that are not very code heavy and the next section in model tuning might seem a little bit more difficult, this is perfectly fine to turn in for the assignment. Just make sure that you explain your work. And there you go. That is how you create a machine learning regression model in Python.